We are back with 11th video in our Webots ROS2 tutorial series. So in last video, which was 10th video and had basics of SLAM Toolbox, we also learned how to add a LiDAR in our custom robot. We learned about overall view of how the project was implemented. So now, after getting all the basics and theory of the project, in this video, we will be learning about how we implemented different files and how you can run a project in ROS2. So at the end, you will learn and you can make interesting maps out of different environments, and you can also use this concept to work on your real robot. We start with bunch of imports. We have RCL.py, timing, RCL.py. We use Webots node, which helps us use Webots functionality. Then we call math, we call some messages. So let's go through init of the class. So we have a class slam enable, where in its init we have a time step variable, which is 32 in our case. So this is 32 milliseconds. We have a timer, like this is a sensor timer. This defines how frequently we will publish the message of sensors. So if you have gone through 6th video, you must be knowing about these sensors. So we have right, middle and left sensor, which are IR sensors. So as we have used here Webot nodes, we can use function self.robot.getDistanceSensor, and when you write the name of sensor, this is the object of your sensor, which is in your proto file. Then you enable it, and then you create a publisher for this topic. Similarly, we do it for mid and left. Also, this is same as our 6th video, where we get motors of our custom robot, which are left wheel, right wheel, front, and these are rear. So we have 4 wheels and 4 motors in our custom robot. And this is new. So we have position sensors on our wheels. They are known as left front position, and I'm getting its value from get position sensor. This is similar to other sensors where we enable by a given time step. Then we have a subscriber to command well. So this is the file which subscribes to command well, and it publishes those values to wheels in order for wheels to rotate in Webots. And this is new, where this is similar to other sensors. So we have a function named get LiDAR, and our LiDAR name inside our proto is LiDAR underscore sensor. So we get LiDAR here, we enable it, and we make a topic to publish our LiDAR data at /scan, and our message type is laser scan. So this is a standard message type which is used for publishing laser data. After which we have some constants and initializations, and we are also publishing odometry. So for odometry, we have a different timer, which is odom timer, and this timer pings every time step, which is every 0.032, which is 32 milliseconds, and it goes to odom callback function. So these are some basics where we have enabling of sensors, distance sensors, LiDAR sensors, and we are also publishing odom. So this was all initialization. So now Let's first of all go through this sensor callback. After every 32 milliseconds, I will get the code in this function, which is sensor underscore callback, which is here. So in callback, we don't do much. We just make a float, which is message underscore write. We get the value from our sensor and we publish the value to sensor publish write, which is this thing, write IR. So we publish our distance sensor data on topic write underscore IR. Similarly, we do it for left and mid. After which we also call a function named laser underscore pub. So let's see this sensor. So when we call this, we have message type as laser scan. We have our frame ID, that means we will have laser scan with respect to base link. If your laser is offset from your base link, you can write here laser link name, and then you can publish a static transform between your laser link and your base link. Then we send the current timestamp. Then in our case, our minimum angle is 0 to 2 pi maximum angle, and we are incrementing at half degree. We have minimum range from 0.12 to 2 meters, where we have not kept minimum as 0 because sometimes laser may be seeing robot as an obstacle. So it's better to clear the robot and then see the surrounding. Here we have scan time to be 32 milliseconds, which is exactly which we saw up. And here we are publishing the data from Webots to our ROS publisher. So you see your self.lasersensor.getRangeImage. So this will give me matrix of laser data around my robot, and which will be published at message underscore laser dot range, and we publish the LiDAR scan. So we are done with this guy where we are publishing to sensor callback. Now let's see what happens when we get a message from command well. So when we get a message from command well, it will come to this callback function, which is cmd well underscore callback. So if you see this is similar to what we had in our video 6, where we calculate the speeds of left wheel and right wheel by the data which we get from our command well, which is linear x and angular z. And similarly, we publish those speeds to respective wheels for Webots. Here we should note that we are also getting value of omega for left wheel and right wheel. So this was about command velocity. And last but not the least is our sensor callback, which is this odom timer. So this timer will ping every 32 milliseconds and it will go to this function odom callback. So when I go to odom callback, I call publish odom function, and here in publish odom we have magic happening, because if you don't do this right, your SLAM toolbox will not work according to expectation. So here we take current timing and save it in a variable named stamp. Then we make a broadcaster, which is dynamic broadcaster, and we take the time difference. Then we take left wheel ticks and right wheel ticks, and then If the difference is 0, then that means our robot is not moving, so our odometry will remain in the same position. If this is not 0, we get the angular velocity of left wheel, right wheel, then we multiply it by radius, so we get the velocity of left wheel and right wheel. And here we consider that both of our wheel can be smashed together to make a single wheel with rotation and translation. So in that case, velocity of my central wheel will be left velocity plus right velocity divided by 2, which is an average of velocities, and my angular velocity will be equal to left minus right divided by 2 into a constant into wheel gap. So if you know the equations of differential drive, you will not see this constant there. But remember, in our case, we don't have perfectly differential drive because we have 4 wheels and all 4 are powered. So we need to add this constant in order to get good odometry. After which we cumulatively add these velocities in our x and y so that we get our odometry updated. So odometry is nothing but how our frame is moving with respect to the wheels. So this is a reset section where we reset the previous values because we need differences here. And after getting all the values, we convert the angles into a quaternion because our standard messages accepts quaternion in terms of rotation. So here I made a transform stamped. I published timing. My frame will be odom frame to base link. Then we publish quaternion here in terms of rotation. We give linear x, linear y, and linear z. So this is a way by which we can publish odom to base link. So here is the publisher, send transform. On the other hand, we also need to publish odometry. So we make a message type of odometry. We take the same timing. We take frame ID as again same odom, base link. And here it's similar where we have position x, position y. And we have orientation as odom quaternion, which is the same. And here we also have velocities. So this is a message type odom. If you want to learn more about odom message, you can Google nav message /odom because it is of type nav messages. So after doing this is all we have in this file. We have a pretty standard main where we make object of our class and we spin the object, and once its work is done, we destroy the object. In this section, we will study about file master.py. So this file, if you have seen our 6th video, this is the same file which we were using for line following. So we subscribe to sensor messages, do some calculation, and publish to command well. If you want to know more about this file, you can go to our video 6, which is line following. If you come here in overview of master, you will get to know the details of the same file. So in last video, we saw about different parameters in SLAM Toolbox. So this is the way by which we can configure SLAM Toolbox repository. So today, in our case, we will be using default solvers. If you did not refer last video, so this is the link of our SLAM Toolbox. So in the documentation, we have details of all the topic parameters which are available for our configuration. We will be using very few of those, and you can use all these parameters to tweak your configuration and get a better result. So let's see, in our case today, we will be using parameters which are solvers. These are bit standard solvers. This file is taken from configurations which were available by the package. So here we changed these parameters where we had our ODOM frame as ODOM, our map frame which package will publish on map. Also we have base frame as base link, and our sensor topic is at /scan. So if in your robot any of these frames or topic names are different, do change the parameters so that your SLAM toolbox will be able to use that topic. Here we need to note that we have a very high resolution. That is why we get a very great map. But if in your case, if you have a LiDAR with less number of rays, you should use less resolution in order to get a better map. And also our update interval is 0.05. So after 0.05 distance, it will start updating our map. As our world is small, we need very quick updates, or else it will miss and we will get a bad map. So there are many other parameters, but for now we are using just these parameters to get the result. After looking at those two nodes, where one node was responsible for enabling all the sensors and another node was responsible for computing command well. So to make our project run in ROS2, we need to add all those information in Setup.py in order to use it through ROS2 through launch files. So we'll look at Setup.py. This also should look similar to the editing which we did in video 6. So we have package named Webots ROS2 tutorial. Then we add launch files, we add world, we add proto. Then we append all the textures which are available in the package. Then here, this is an important location where we add our file name. So in here we have Webots ROS2 tutorial folder in which we have slam_enabler.py. This will be assigned by a name which ROS2 will understand, which is slam enable. So for the matter of fact, if I see launch file, I will just see the executable name which is made in our setup.py. So these are the details which we need to enter in setup.py in order to make our project run. And finally, we will have a look at our launch file, which will be calling all our nodes and which will be responsible for as a starting point for our project. So we have some standard imports here. So here basically this is similar. Again, this is similar to project which was in video 6, where we had two files to be executable, one being Webots, which is responsible for executing my world and also Webots node. And we have an independent node which is our line following node. So these are two nodes which we put in launch file, and then we pass the names of these two nodes here. So our first node is Webots and second node is line follower. So this is pretty much same. If you want to have much more details, you can visit again video 6. Now, last but not the least, let's build the project and let's run it. So first of all, let's open our terminal and go to our workspace. Then we will click colcon build. When I hit on enter, it will build our project, and you see here we have Webots ROS2 tutorial. So our package is correctly built. Now we will source it. So we will source install setup.bash. Similarly, we will source in all the terminals, which I have already sourced. So now we will be using this launch file. So in our case, we will be using ROS2 launch, Webots ROS2 tutorial, slam toolbox _ launch. Also in our configuration, so we will go to ROS2 workspace, source Webots ROS2, Webots ROS2 tutorial, and we have a config folder. So if you see here, we have a slam config, which is exactly this one. So now we will run a command which is ROS2 run slam toolbox async slam toolbox _ node, and in our ROS argument we will give use sim time equal to true, which will enable this package to use our simulation time, and we are using parameter file as slam _ config.yaml. Don't worry, this command will be given in the description. So now when I hit on enter, you see our solvers are correctly plugged in, and this package is ready to accept the scans. Then let's on our ROS2. There you go. So we have ROS2 on. Now in our case, we will go to file, open config. So in home, it's my ROS2 workspace, source Webots tutorials. Where did you go? Here you go. And in ROS, we have a configuration already saved, which is known as slamwiz. So if I open this, close without saying, you see this configuration is already ready, and I can see ODOM and map link. After which we will on our node. So when I on it, we see our thing, but most interesting is our ROS, where we are seeing the odometry. So now you guys must be relating that we sent two things, one being odometry, which is the red in color, and one we send a transform between odom and baselink. Here slam toolbox is doing a great job in terms of shifting our odom so that our scans match our map. So once it's done, we will again see our Webots, where you see here these are the obstacle, which is one is box, one is again a box with a tilt, and one irregular shape. So these are the things which we should see in map, which we are correctly seeing. We use line following. You can also use keyboard if you want in order to move your robot, and will result into similar output. So you see here our map has a square shaped black line, but in our RVs we see that our odometry is taking somewhat triangular. So here in this case our odometry is not perfect because you saw in our files we assumed that our four-wheel drive is like an differential drive, but actually it is not. That is why we are seeing this slip. This is usually the case in real robot where you don't have perfect odometry. So this is a great tool to get a map. So if I hide our odometry, you see this map. And now we will learn how to save our map. So now let's learn how to save the map which we made from slam package. So for this we will need to close our Webots node, and then if we do ROS2 run nav to message saver map saver underscore CLI and specify the topic name as -t space map. If I hit on enter, yeah, it successfully saved the map. You see here, if I ls, I can see a map and a YAML file. If you want to see the detailed map, this is the map which we got. You can flip it however I want. And it also gave us the YAML file which gives us origin of map, which gives us the resolution and also the threshold of occupancy and free. So those of you who know how the map server works, they will know that these are the parameters which we need in order to place our map in ROS2 environment. So this was all about today's video. Hope you like the project, and if you like it, share it with others. And the question for today is, what was your implementation of Slam Toolbox library? I would like to hear you guys in the comment section. So do like the video. Bye bye.